You just knocked over there.
All right, good morning, everyone. So today it's going to be the last bit of the theoretical part. So we're going to talk about something called the line arc method. We're going to introduce the principles behind the line arc method, and then I'm going to go through an example in Abacus on how to model an unstable static problem. And by unstable, I don't mean that the structure is not restrained, but I mean an unstable, I'm talking about a problem where force versus the structure response has a negative slope. And we really don't know what this maximum force is. Let's call this F max. We don't know what F max is, and we're interested in the response of the structure beyond this maximum force. Because we're interested in the response of the structure beyond the maximum force, we need a method by which we're able to solve without actually knowing what the external load is. The Newton-Raphson method is able to, if this is the force and this is the response, the Newton-Raphson method is usually able to do the following. If I employ the Newton-Raphson method and I apply this force, the Newton-Raphson method, or any software, will start with an initial point, apply a small iteration, a small increment, reach this point, reach this point, reach this point, and so on. Trace this curve until the maximum. Once it reaches maybe here, it can reach, all of a sudden the increments will become very small, and the program will stop because it can't go beyond this maximum point. Simply because every time, as you've seen in two assignments before, at this location, when I'm doing the Newton-Raphson method, calculate the slope, reach here, 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 and you'll never reach any equilibrium or any convergence, and so on. So it will get stuck, and you won't be able to pass the peak point of the force displacement curve using the traditional Newton-Raphson method. And so we need another method that's able to solve, or that's able to follow the response of the structure once it softens, or once it becomes unstable under load control. So this is unstable under load control, or softened structures. So let's talk about the applications of such, if such a method exists. The most important application is buckling. And post-buckling behavior. So what is that? What happens in buckling? What happens in buckling is that you have, for example, a load displacement curve of this structure. You are applying a load on this structure. What happens initially, let's call this delta. Initially, the structure is very stiff. You're applying P, the structure is deforming only in compression, it's very stiff. And then it reaches a point at which it starts, after a certain critical delta, it starts buckling, and then the delta becomes larger, so you get some sort of a softening at that instant. And depending on the structure and the elasticity and the plasticity and whatever material properties, it might just keep going down, or it might actually catch up and go up again. Whether it goes up or down, I'm interested in this. I'm interested that whatever method I use to overcome this softening behavior, because if I use the Newton-Raphson method and I'm applying this force, once I get to this point, I will probably be stuck. Or I might even, the structure, the software, might even give me a response that looks like this. This is initial point, another point, maybe a point here, maybe a point in the peak, maybe this point. And so you will miss that gap or that decline in the force versus the response curve. Now, if you have a structure with one force on that structure, you don't need to do to apply loads, because for this particular example, so if the load is applied at one point, if the load is applied at one point only, you don't really need to apply a load. You can apply displacement. If you apply displacement, this structure is stable under displacement control. Because it's stable under displacement control, you can actually apply the displacement and measure the force. So if you apply displacement and measure the force, you'll be able to track this response. Because you're applying displacement, not load. So if the load is applied at one point only, you can perform displacement control analysis, which will converge for a softened structure. what if I know the load is applied. See, if the load is applied at one point only. So what if the load, for example, is applied I have to, not if the load is applied at one point only. Let me just rephrase this. In certain situations. In certain situations. So let's explain what I'm talking about here. And we will talk about the problem in your assignment. So let's look at this structure under this load P. Under this load P, I'm drawing the P versus vertical displacement. For this particular example, it's possible to apply the displacement and measure the force. So apply vertical displacement and don't worry about the horizontal displacement. Let the structure move horizontally wherever it wants. Once you apply the displacement, you can measure the force, the output from the structure, the FE will give you the force, and you're able to track the response. If, on the other hand, you have a force here, P, and you're interested in the vertical displacement delta, you're not able to apply this vertical displacement delta because you have the ratio between, you have a known ratio between PA cosine theta and PA sine theta. Where this is theta. So for this particular example, I'm not able to apply displacement. But what I'm able to do is apply force, PA cosine theta, PA sine theta, and try to track, I'm trying to find a method at which I really don't know what load I can apply on the structure. So for these methods, I don't really know what the maximum load that I can apply on the structure is, but I just want a method for which I can keep increasing PA or changing PA, and I can follow the response. Now these methods are called, in Abacus, the method that does that is called static Ricks method, or in general, line arc method. So these methods are used under the following conditions. The load vector on the structure is not known. Let's call it the magnitude of the load vector on the structure is not known, but the direction is known. Example, I have this structure, I have a P and a moment that's equal to M moment that's directly proportional to P. For example, M is equal to AP, where A is constant. So I have the ratio between P and AP, so I know that the load, all the load applied on the structure is function of one variable. I know the direction of the load vector, but I don't know the magnitude. I don't know what the value of B is. If I have the value of B, then I'm able to draw the response of the structure, but the response of the structure as a function of P has this behavior, and so I'm not able, I really don't have a value for that P, because I don't know what this maximum value is. So in order to solve such a problem, we will still employ the Newton-Raphson method, but we also will we will need another equation to solve for this unknown P. So, given the response, since you don't know what the applied P is, you can apply whatever you want. And this is called the applied load, the load that you apply on the structure, and this corresponds to something called the load proportionality factor of 1. This is the full load that you applied on the structure. This load could be really close to the maximum, or it could be really far, it doesn't really matter. You're just applying basically the direction of the load applied on the structure. And let's say you are at this increment where this is lambda naught corresponding to x naught. So let's say lambda naught, for example, 25%. When you apply the 25% of whatever maximum load that you apply on the structure, you get this response. The next point is obtained since we don't know the load, we have to have an extra equation. So we have our equilibrium equation. We solve the equilibrium equation to find. We are solving the equilibrium equation using the Newton-Raphson method to find the displacement, but we actually don't have the applied load. So the applied load is another variable that can be obtained by defining or by restricting the increment on this load displacement curve, the length of that increment, and that's what we call the arc length. By restricting how much we can move on this curve. So, sum of forces equals 0, that's first, or equation in displacement variables. Now the extra equation that we need to solve is we fix this arc length at r. It shows in value 0.1 or whatever value. Usually the software chooses this value. And you restrict this length. Now this length is equal to the square root of delta displacement and delta L. So delta lambda squared plus delta U squared, where U is the response. But sometimes the load proportionality factor, if you apply 1 Newton, but the structure can take 1,000, then your load proportionality factors can be 1,000 minus 1, so you get huge numbers here. And the displacement could be in millimeter, and so you get a very small number here. So this equation would not be balanced. So to balance this equation, you have to normalize delta lambda, and you have to normalize delta U. Otherwise, you're adding 1,000 squared plus 0.1 squared, so this wouldn't really have any effect. So to have this equation balanced, the unknown lambda minus lambda squared divided by, let's say, lambda max plus delta u squared, which is, let's say, call this y minus x naught squared divided by a normalizing number so all these are known, lambda squared and r, x naught, lambda naught, and what we want to know is y and that. So, an example. F of x is equal to negative 0.0 x cubed plus 1.2 x squared plus 3x. When you plot the load versus the force versus, or f of x, sorry, versus x, you get this response. And so we're interested in using the line arc method to trace that curve. And let's say we're starting from an initial point where lambda naught is known to be equal to 0.4935 and x naught equals 7. And the force that I'm going to, or the F that I would like to apply on the structure is 120. So this is equivalent to 59.22 over 120. Because lambda max is equal to 1, corresponding to a force of 120. And lambda naught is equal to 0.493, corresponding to a force of 59.22. So the proportional of the load, the amount of load that I'm applying is 49%. So the equation that I'm looking for is that f of y is equal to lambda multiplied by 120. In the traditional Newton-Raphson method, I don't have this lambda. I would say I'm looking for y such that this function is equal to 120. But because this 120 is kind of almost arbitrary, it's just a direction, not a value, I'm utilizing a load proportionality factor lambda, which is unknown. So this is one equation. I need another equation to find this lambda. The additional equation is, starting from this initial point, I need to restrict the length of the arc drawn on this curve, which is the ratio between delta lambda. I want to restrict the ratio between delta lambda and delta u. So equation 1, negative 0.06 y cubed plus 1.2 y squared plus 3y minus 120 lambda equal to 0. This is equation 1. The second equation, the square root of lambda minus this initial number, 0.4935 squared, divided by a normalizing factor. Here is 1, plus y minus minus 7 squared divided by 20 squared, and this is given to you for this particular problem, the normalizing factor, and is equal to an arc length, and let's restrict this arc length to 2.1. Now these are two equations in two unknowns. Now you can now utilize the Newton-Raphson method, because these are nonlinear equations. Utilize the Newton-Raphson method, find root, or do it by hand, find root, equation 1 and equation 2 are both equal to 0, and solve for lambda with an initial value of a little bit higher than, let's put it 0.4935, and let's put y, let's give it an initial value of 7.1. Why 7.1? Well, because I have 7, I'm starting with initial 7, and I'm moving 0.1, so an approximation is 7.1. So when you do it that way, you would, this is what you get out of it, point, 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 and all these, the length would all be constant, or depending on how you normalized it, you just have control over that length. And so you get those points on the curve. Now, in your notes, I've given you the code on how to do this in Mathematica, and also a point of an important point is the initial guess makes a big difference in the response, because the Newton-Raphson method really depends on the initial guess. If you don't put the right initial guess, you might not get the right response. What happens in these methods is that you might jump from this point to this point, and right here, sometimes, which you can even notice when you do buckling analysis in finite element analysis software, because the direction of the load is not given, you might find that you're tracing the curve backwards, because you're drawing a circle here. So this point and this point satisfy this circle. Because this point and this point satisfy the circle, sometimes you get the response, you get you trace the curve backwards. You trace it all the way up to the maximum point, and then when you reach the maximum point and you draw that circle, the curve is traced backwards rather than forwards. So it really depends on the initial guess for for those vectors. So the fun problem is the one in your assignment. It's really fun. So let's first, so in your assignment, I'm asking you to solve this particular problem. This is a structure that's stable in this shape. I would like to apply force P. Let's call this 1 meter. I don't really know what force I can apply. All I know is I want the response from here to here. Now if you do it by hand, you can apply the displacement. You can apply vertical displacement and find the force. But I want you to use the line arc method by hand. Now, if this, let's call this 0. Let's call this U1. Now let me draw something for you. Let me give you a hint. At U1 is 0, the force, the external force is 0. And at U1 is equal to 1 meter, 2 meters. the external force also is 0. Because basically these two bars, if they're here or here, you don't really need any force to keep them at this location. It's just this is the hinge, so whether you're here or here, the external force is 0. Now what do you think the response in between looks like? So just draw it, and then just draw it now, and then I'll show it to you. Draw it. Okay. Well, let me see. Let's see how clear it is. So you're telling me that the vertical force is maximum here?
Yeah, and 0.
Maximum and 0?
Like it goes to max and then drops if the whole thing snaps down.
Okay, so you're saying there is a point of discontinuity? So draw the curve. Well, at the top, the force is 0. Okay, let me give you another hint. At this location, at this point, what's the direction of the force? Upwards or downwards? Down, to keep it stable.
It seems decrease and suddenly it is unstable.
That's right. I mean, that's why we're doing this kind of analysis. Because I want to get the response, the static response at every moment. So what happens here is that at this location, actually, the load for this particular displacement, these want to move down, so you have to keep them up. So the force is actually changing its direction. So the force that's carried by that structure at this point is actually the opposite. So, and exactly at 0, it's true 0, but the response of the structure looks like this. Did anybody draw it like that? So the actual response of the structure looks like this. And so you're required now to solve this problem. So how many equations are there? So assuming P is equal to 1, or the applied P, you apply P of 1, so lambda and lambda max is equal to 1. So in terms of displacements, how many unknown displacements do we have? 2 displacements, horizontal displacement U1, because these two are given in the problem with different lengths. The two bars have different lengths, so you can't use symmetry. And so you have a horizontal displacement U1 and a vertical displacement U2. These can be found by saying sum of forces in the horizontal direction equals 0, sum of forces in the vertical direction equals 0. And sum of forces in the horizontal direction would be F1, F2, theta 1, or theta 2, theta 1. These are all functions of the displacements because you have the strains and the length and all that. Similar to the problems that we solved before. So for example, F1 is equal to E multiplied by the area multiplied by the stream. E multiplied by the area multiplied by the new length minus the original length divided by the original length. And the length is the square root of, right here you're going to find U1 and U2. And so F1 cosine theta 1 plus, or whatever, depending on the choice of your signs or convention, plus F2 cosine theta 2 is equal to 0. Equation 1. Equation 2 would be F1 sine theta. Maybe this will be negative. F1 sine theta plus F2 sine theta 2 minus lambda p equals 0. Lambda p, because I don't know what p is. I don't know what the load is, so I need a third equation. The third equation is the square root of the following. Lambda minus lambda naught squared divided by lambda squared max. And I tell you choose one for this particular one, plus, I think I give you what normalizing factor you use for this, u max. And here, you have to use delta u1 squared plus delta u2 squared equal to r. And in the problem, I give you r as well. Initial point, lambda naught equals 0, u1 equals 0, and u2 equals 0. And for initial guesses, every time you find an increment, you need an initial guess for the next increment. The initial guesses use lambda from previous increment. All right, so in the next, this is it. This is the last bit of all the theory that I want you to know, or all the hand calculations that I want you to know for the finite element analysis. For the rest, well, actually, in the next lecture, I will also cover a little bit of hyperelastic materials. But for the remaining part of today, I want to show you how to model buckling in finite element analysis software. Of course, I'm using Abacus, but everything that I do in Abacus can also be done in ANSYS and in any nonlinear finite element analysis software. So I'm going to show you exactly how to do your assignment. For your assignment, I've asked for the following. I've asked, this is the first problem, and the second problem is as follows. is your first problem, and I already give you the solution, so this is what you expect to see. And for the second problem, what we're interested in is, if you have a pipe, we're interested to see, to draw the relationship between the end moment and the rotation. So I have a piece of pipe, and I'm going to apply a bending moment at the end of that pipe, and I would like to draw the relationship between the rotation and the applied moment. Now I don't know at which point this pipe will start to buckle, because at some point it will start to wrinkle or buckle, and the external force will decrease. It might increase again, but I don't know how much that load is. So I'm interested to draw that relationship. And I would like to compare two conditions, where I have an internal pressure inside the pipe, and another case where I don't have an internal pressure on the pipe. So let's, I'm going to show you the solution. So the unpressurized pipe will do the following. As you start, so this is, I'm utilizing a quarter of the pipe because it's symmetric. Now I'm applying bending moment here. As it buckles, I can use quarter of the pipe to model the whole thing. It's symmetric around these lines and this line, and the load is applied at this point as a bending moment applied on the whole end. And the final shape looks like this. So you can see as you apply bending here, the pipe deforms and buckles at this point and buckles to the inside. Now, when you put internal pressure, you get a different response. I think there's one. It buckles to the outside rather than to the inside. That's because the internal pressure is actually pushing it out rather than in. Now, if I increase this analysis, then this would wrinkle, would have a big wrinkle, and would be buckling to the outside. Okay, so how can I model something like this? Now the response, now since I'm showing you the results, now what I'm interested in is what is the load and what is the rotation at this node. So I don't know the load. I apply the load of, I don't remember that, let's say 10 power 9. But this 10 power 9 is just, is not the actual load of the structure. The actual load of the structure is the load proportionality factor multiplied by that load. So the load proportionality factor is a history output. Load proportionality factor plot, and you can see for this particular structure, when you're applying whatever number applied, it's increasing. At some point it starts decreasing, and then it's kind of horizontal. So after it starts buckling, as the moment is increasing, the moment is not increasing, but whatever the displacement is increasing. And so for this, I'm going to report the load proportionality factor. I'm going to call it LPF. I would like also to draw, because I'm interested in the load versus rotation. So this is a field output, unique nodal. I'm interested in the rotation. The rotation, I apply the moment around 1. Rotation 1, and I'm going to show you how to set up all this. And I'm interested in this node. But so, because I'm applying two different, for the one with the internal pressure, I have, first I'm applying internal pressure, and then I'm applying the buckling. I would like that the output can only be done in one or the other, and I will explain why when I set up the model. But I'm just applying, I would like the output only in bend. And so you can see the angle is increasing, but the load did not. So I'm going to report this. I'm going to call it displacement. And now if I can open them using Excel. And so you can relate both values using the first variable, which is the arc length. So I'm going to copy this into displacement. So this is the rotation, and this is the load proportionality factor. The actual load on structure or moment is equal to this multiplied by whatever moment I applied. Let's say I applied 10 power 9, I think, Newton millimeter. So this is the actual load on the structure, and the actual, the end rotation is equal to this value. And so you can plot the moment versus rotation. You can see that the initiation of this is elastoplastic buckling. The initiation, this is the model plastified early, but then at some point it dipped, and then it was moving horizontally where the rotation is increasing, but the moment is not increasing anymore. What you will find different between both is the pipe without internal pressure will buckle much earlier in terms of the displacement response, will buckle much earlier because the internal pressure stabilizes the pipe. So the internal pressure stabilizes the pipe. The pipe without internal pressure will buckle much easier. And you'll get a response that is, you'll get a response where the pipe will buckle much earlier. Alright, so are you guys following? Would you be able to export, if the model is run, would you be able to export these things? Okay. Alright, so how can I now model something like this? So, usually when you're modeling something, especially with buckling, you want to initiate some initial imperfection to basically guide the buckling, because the buckling usually can happen at any point. Buckling could happen here, the buckling could happen here, or could happen closer to that where the load is applied. So to guide it to happen here, I have to apply a little bit of an initial imperfection. And for this particular problem, I chose a small area here where I made the wall thickness of the pipe slightly smaller than the actual wall thickness of the pipe. So the actual wall thickness is 10. I chose a small area here where I made the wall thickness as 9.75. Just to make sure the buckling will start here rather than at the other end. If you don't do that, you'll just end up buckling perhaps this area because of the stiffness at this end, because at this end we're going to model it as a rigid end. The moment is applied on a rigid end. So how do we do all this? So I'm going to show you a few things here. The first is how to create the model, how to apply a rigid end, how to make this a rigid end, and how to choose an area and give it a smaller cross section. So I'm going to start a new model. First I'm going to create a part. This is a 3D. It's a shell. It's extrusion. And the approximate, the diameter of the pipe is 1 meter. So I'm going to put here 1 meter. And I'm only interested in quarter of the pipe. So I'm going to draw this, first the whole diameter of the pipe. And then I'm going to trim. So I'm going to trim this piece. I don't need this piece, nor this piece. And I'm going to delete these lines. So this is the quarter of the pipe that I'm interested in. The length of the pipe that I'm modeling is 4 meters. So I'm only interested in half, so this is 2 meters. So this is the quarter that I'm interested in modeling. I'm going to apply the moment at this end, and I'm interested in making a small section here, maybe 20 centimeters. Give it, maybe 22 centimeters or some, just to give it a slight thickness variation. So to do this, I have to make my part to partition my part. So to partition my part, first I have to create something to partition it with, and you have here lots of tools to partition parts with, but here I'm going to choose a datum plane, because I know this is the XY plane. I'm going to offset this XY plane. I know, because I've done it before, I know this is the 0 point. And so I'm going to offset this with about 180. And I've created an offset plane, a datum plane at this location. It might be too close. perhaps make it 1950 rather than 198. Yeah, that's fine. So I'll just choose a bigger section at which the thickness will be smaller. Okay. And then, just to make sure that the buckling starts here. And then the next thing is to do the partition. So I'm going to partition face using datum plane. Select the datum plane, it's that one, and create a partition. And you can see now I have two connected parts. It's one part, but just connected at this line. And because I have those two parts, I can apply a section here different from the section here. I'm going to mesh it. Let's say 20. Shell elements. I can mesh these with different elements, but both will be the same type of element. S for R. Okay, to mesh part, yes. The materials. So mechanical. Elastic. The elastic portion is 200,000. Poisson's ratio is 0.3. And the plastic, you're given the same curve from last time. So 0 and so on. So I'm not going to put it all, just assuming that. So the same thing similar to the previous assignment. It's a plastic, elastoplastic buckling. And I'm going to create section 1, shell. And the thickness is 10 millimeter. And I'm going to create another section 2. And the value is 9.75. Then I'm going to assign sections. This one. This will take section 1 and top surface. Why top surface? Because I give you the diameter. This is the outer diameter. You could have just used the average diameter, not the outer diameter, and use this middle surface. And choose this one, section 2, and top surface as well. So if I now look at view part display options, if I render the shell thickness, you'll see slight difference between this one and that one, and the shell thickness is inwards because I defined the diameter out, the outer diameter. You could have defined the average diameter. So we have the mesh, we have the materials. Now we're going to bring everything to the assembly. And we're doing 2 times 2 analyses, one with internal pressure and one without internal pressure. So I'm going to show you the one with internal pressure. So the one with internal pressure, you have to create 2 steps. But there are boundary conditions that will never change, which are the symmetry boundary conditions. So I'm going to define this in the initial stage. In the initial stage, I have symmetry boundary conditions. This area is symmetric around Z, or on the plane perpendicular to Z. And this area is symmetric around X, around the plane perpendicular to X. The next step is a static. General, just applying internal pressure. I'm going to call it pressure. everything is non-linear in the geometry, the pressure, usually the internal pressure in a pipe is to cause 80% of yield stress. So I'm going to explain this in a second. So non-linearity in the geometry, the pressure is usually small, so I'm not really in the plastic zone. Because I'm not really in the plastic zone, I can just use it, apply it all in one initial increment. So in the boundary condition, in the load, I'm going to apply pressure on this surface. And because it's a shell, the pressure could be on the outside or the inside. I'm going to apply on the inside, which is the purple. And the magnitude is 12.8 MPa. How did I get that 12.8? The 12.8 is equal to the volume. Usually this stress is equal to 80% of the yield, which is 80% over 100. That's the maximum stress that a pipe is designed for. 800. That's given. This is due to the internal pressure, which is equal to pi multiplied by the outer diameter, P multiplied by the outer diameter divided by 2t. The outer diameter is meter. The thickness is 10 millimeter. And so you get that what internal pressure should be applied. Alright, so we applied the internal pressure, so we pressurize the pipe. Let's just make sure that everything runs smoothly. Now maybe before that, let's fix the end. Let's apply a constraint, what we call a rigid body constraint. I want to fix a whole area to one rigid point. Now to do this, I have to first define the rigid point. So I'm going to define the rigid point. I'm going to go tools, called reference points. And there is a point defined here, so I'm going to choose this point and make it as a reference point. So now I have a reference point, but this reference point is not tied to anything. I'm going now to tie this reference point to the whole surface. So I'm going to go to the constraints, a rigid body. I have a rigid body made out of the following nodes. I'm going to tie these nodes to one reference point. So anything that I apply on this node is applied rigidly on this whole surface. So now let's fix this end. So now I'm going to fix the rigid point. And just let's make sure that this job runs. Submit. If you miss anything, you can let me know, I can repeat. And it was applied. So the status file, it was applied in one increment, and it was successful. And if you go to results, if you look at the von Mises stress, it's exactly So it's yielded at this location. It's actually reached the yield right here. But in general, far from this constrained edge, the stresses are around 80% of the SMYS, or the specified minimum yield strength of the material. And because shell elements have two sides, so you have the stress throughout the whole thickness of the shell. Usually, it's important to realize that you should plot the envelope of the stress on each shell. Okay, so here's after the initial step. Now let's create another step, the bending step. So this other step is not a static step, it's not a general step, it's static breaks, which is what Abacus uses for the line arc method. Now since there's no end to this analysis, you can specify what is the maximum load proportionality factor, or you can specify a maximum displacement at a particular point, or you can just let it run. This is the arc length increment, the initial arc length, the minimum and the maximum. This is the which is the delta, the R that we talked about. Okay, so step 2, let's just call it bending. Really, bending. And for this step, first the boundary condition, the third boundary condition, will have to be deactivated, which is the boundary condition on the rigid point, because now we want to apply bending on that rigid point. I'm going to create another boundary condition. I'm going to pick that rigid point and fix everything except the rotation around 1. So I'm fixing that endpoint, but I'm going to apply a moment. Now for this particular problem, you are able to just apply rotation, and you don't have to apply force. Because if you apply rotation and measure the output as the force, you'll get the response that you want, just for this particular problem. But I would like to apply load. That's a moment. At this rigid point, and that moment is around 1, and I believe, now if you put a very small value that's really far from what the structure can take, you might never achieve convergence because everything would be 0. So you wouldn't get any iterations. So for this particular problem, I think that an appropriate value, but do a calculation just to get a good value for the stress, the appropriate value is about 10 power 8. 4, 5, 6, 7, 8. And let it run. Now, it will take a while, so here's it starts to bend, but it's going to take a while to apply all the bending. And that's it. That's how you can model this. The other one you would just model without the internal pressure. You wouldn't have that second step of the internal pressure. You just only have the bending step. So this is it for today. I'm not expecting you to. This will take a long time. Even though I did it here, it will take a long time. Just don't wait until the weekend to get it done. Okay, and you have the videos, or you can put the video on the side and try to get it done, but just try to understand what you're doing. Because you are going to need this. I don't know what, each person will have a different project. But any of the things that we did here, you might need it for your project. Defining, creating parts, making parts smaller, making something that's creating a rigid end, applying a force on a rigid end, applying moment, using the line arc method. So depending, all these things are tools that you can use for your own project. Now in the next 2 lectures from now, because next weekend is off, perhaps maybe before I let you go, I'm just going to start talking about contact. So 2 weekends from 2 weeks from now, I'm going to give you a tutorial on how to use contact. But if you want, who's going to use contact for their project? Who wants me to show you now how to do contact?
What's going on?
Contact between parts. Contact. Okay, well, if you guys don't want it, but I'll have to show you how to do contact, just in case you need it for your project. So you have the tutorial already, but let's do the same. Let's have the same. Everything is the same, but let's now drop a big cylinder on top of this pipe and see what happens. So I'm going to kill this. So instead of this bending case, I'm going to take that bending away. I'm going to delete this bending. I'm going to create another part. Let's make it a solid 3D solid revolution. Let's create a let's create a ball of metal that's going to fall on this pipe. So, mesh. Using linear, that's fine, I'm going to use linear element here and mesh it. And that's fine, I'm going to use that mesh and mesh it. Okay. So I have this ball that will fall on top of the other one. Let's partition it. So let's pick XZ plane with a 0 offset, and let's partition it. mesh it again. Okay, so I have a vertical. I have a partition just so that I can apply the load. Now I'm going to bring this part into the assembly. Part 2. Where did it go? Now I'm going to drop this on top here. I'm going to move it. From this point to this point. Okay. And then, well, let's drop it inside. Just drop it on this. And so I need to define contact. So interactions. Surface to surface contact. One is a master surface and one is a slave surface. Usually it choose the more rigid as a master surface. So I'm going to choose this as a master surface. And the slave surface, I'm going to choose this and this. And which side of the shell elements? It's the purple side. So you have a few things here that you should look at. If you're starting with the two surfaces already in contact, you might ask the software to do some adjustments so that the initial nodes are in contact. Or so if you have a little bit of penetration, if there's some numerical issues where you're modeling two surfaces, one node is already penetrated the other, one node has already penetrated the other surface, you might want to bring it back. So this is to adjust the state, but we don't need any adjustment. And for any type of contact, and I'm going to go through this again in more details in 2 weeks, but for those who might want to do this for their project, or starting the project, they might want to take note of what's happening here. So to define contact, I have two properties that I need to define. How things contact perpendicular to each other, and how things contact, what's the property of the contact as things start sliding on top of each other. So I'm going to create a property, interaction property, and define two aspects: the tangential behavior and the normal behavior. The normal behavior, the hard contact, and I'm going to allow separation after contact, and I'm going to explain the difference between all these in 2 weeks from now, but for now, hard contact is usually good enough. And the tangential behavior, frictionless or penalty, using the penalty method to enforce the constraint, and you put a friction coefficient, but for now let's put frictionless. You can use the penalty method, or you can use the Lagrange multiplier method. So let's use the penalty method, for example, and put a coefficient of friction of 0.3. So now I have two behaviors, the normal and the tangential behavior. So let's go back to our steps. In the first step, I'm going to add a boundary condition of I'm going to fix this ball in space here. And then after applying the internal pressure, I'm going to apply a displacement, static general. I'm going to incrementation. I'm going to make it in steps of 0.1. make it 0.5 first. So I'm going to bring this top part. I'm going to move it down, so U2. Everything else is 0, but U2, let's move it down about 500 millimeters.
So you need to be negative.
You're right, I'm sorry. Negative 500. And the boundary condition 4 has to be deactivated. And now let's run it. Oh, I didn't define anything for the wall. So let's just give it the same material properties. Just have to create a section, a solid section, and assign So you have here a warning, there are two unconnected regions in the model, because at the beginning these two parts are far from each other, and just the software is letting you know that, remember that maybe you know of it or not, but here's that you have two unconnected regions in the model. So let's look at the results. So this is the first. As you drop the ball, now I chose to apply this as a displacement because I have more control over displacement. Everything will be more stable when I apply displacement rather than applying a force. If I apply a force on a ball that's in space, it's never going to solve, because because there's no reaction to it. If I apply a force on it, I'll never achieve static equilibrium. So I chose just to move it down with displacement. And so, as expected, the first step, 0.5 of the full displacement worked. When I tried to apply another 0.5, it didn't work. When I tried to apply 0.125, it also didn't work. It was too much displacement. And finally, small displacement worked. Let's see where we are now. Still getting closer. Getting closer.
So the one tells you the string increment will exceed 50 times string because the first you. I get the same only message.
That's when you're trying to apply the load too fast.
No, actually I'm not very fast. I'm 0.0001 of my increment. It's still getting this message. I don't know why.
Yeah, with contact, you have to establish contact very slow. So in problems like this, you would just move it all in one step, such that they just barely touch, and then you start applying whatever displacement load you want. Because at the beginning, the software doesn't know which node is touching which node. So it's going to take a short while. I'm just going to give you 5 minutes until I solve it.